What's up, everyone? Today, let's try to do some math for fun. We're going to evaluate the finite sum of the natural numbers. Namely, we're starting from the first term, 1, plus 2, plus all the way down to the nth term. Okay? I know most of you probably already know what the answer is, but let's say if we don't know what the answer, how are we supposed to find it? Well, back in the 18th centuries, Gauss has already provided us a method of adding the finite sum of the natural numbers. And the way that he did it is, he will actually try to pair up the terms in a special way so that the sum of each pair will be the same, and then we'll be able to find out the formula. So, if we generalize it, let's call this S. Let's see what we can do. Since we have a finite sum, meaning that there are finitely many terms, we are allowed to rearrange the order in however we want. So let's try to rewrite this backwardly. Namely, we're starting from n plus n minus 1, and then with a decreasing order, all the way down to 1. And don't forget, this is still the same sum as we have, S. How is that going to help us? Well, let's try to add the two equations together and see what we get. So on the left-hand side, we just get S plus S, which is 2S. Nice. On the right-hand side though, now we can try to add up the same terms together, meaning we can add the first terms together, giving us n plus 1. And then if we add up the second terms together, it also provides n plus 1. And if we keep doing it, we see that eventually all the terms will turn into n plus 1. And now, remember, we said that there are n terms in each sequence. Therefore, here we end up with n copies of n plus 1. It means that now we actually get n times n plus 1. So, to find out the actual sum, we just need to divide 2 on both sides and get the final answer. Ta-da! We now actually get the result, which is same as the one that we actually, which is same as the one that we know about, which is same as the one that we know. And here is the sum of the natural numbers from the first term all the way up to the nth term. We actually get n times n plus 1 over 2. Excellent. But this is actually not quite interesting, right? I mean, we already know what it is. We're just trying to check how we get it. So let's try to play around with it. What if we're going to increase the power this time? For example, if we're going to raise it to the second power, namely, we're adding the sum of the square numbers. What do we get? Well, perhaps most of you already know what it is too. And even if we try to raise it to the third power, I bet a lot of you also know what the closed form is. And most likely, you actually have taught by your teacher what the closed form of the finite sum of the natural numbers, square numbers, and cube numbers are. So, great. What happened if we raise it to the fourth power? Okay, here we go. First, let's consider this expression here. If we start with n plus 1 to the fifth power minus n to the fifth power, by binomial expansion, we know that this will give us the following coefficients: 1, 5, 10, 10, 5, 1, where the first term will be multiplied with the n to the fifth power, and then the next term is n to the fourth power, so on and so forth, until the constant term. I know it looks like there is 51, but again, these are actually two different coefficients. And then don't forget we subtract the n to the fifth power, meaning the first term will actually be cancelled out. So we end up with the following: 5n to the fourth power plus 10n to the third power plus 10n squared plus 5n plus 1. Great. How's it going to help? We can't already tell yet, right? Let's do a few more. Next row, I'm going to put n to the power minus n minus 1 to the power. So now we can replace n by n minus 1. Meaning we're going to get 5 times the fourth power of n minus 1 plus 10 times the third power of n minus 1 plus 10 times the quantity n minus 1 squared plus 5 times n minus 1 plus 1. It's not big at all. But if you keep going, we'll eventually get all the way down to the power minus 1 to the power. You can go a little further, that much row, but it's not necessary. And you'll see why it's not necessary later. You keep going, we get all the way down to 1 to the power minus, let's take a look. What do we end up with? 0 to the power, there we go. And then now we get 5 times 0 to the power plus 10 times the third power plus 10 times 0 squared plus 5 times 0 plus 1. So let's see what we get all that together. Okay. So doing this, first let's count how many rows we have. The easiest way to check how many rows we get is, let's say we take the last row, because we start with 1 to the fifth power. Let's call this row number 1, and we're going to count upwardly. So we have 1, 2, 3, all the way up to n plus 1. So we end up with, so we have n plus 1 rows overall. How is it going to help? Let's take a look on the left-hand side. On the left-hand side, besides the n plus 1 to the 5th power, everything else can cancel out. For example, here we have n to the 5th power with a minus sign, and on the next row we have plus n to the 5th power. Those two can be cancelled out. Similarly, the n minus 1 to the 5th power will be cancelled with the n minus 1 to the 5th power in the next row. And we can keep going until we hit the last row, which the plus term will be cancelled out, and leaving us with the minus term. And this is actually known as the telescoping method in math, meaning that we can just turn the whole a long sum, or sum with many terms, all the way down to something very short, just like how a telescope works. So if we simplify the left-hand side, we just get n plus 1 to the 5th power, minus 0 to the 5th power, which is 0, so we just end up with minus 0, which is not going to affect it. Great. On the right-hand side, first, let's factor out all the common terms. Meaning, we're going to factor out the coefficients. So here we can factor out the 5. On the second column, we can factor out the 10. And then we can also factor out the 10 here, factor out the 5 here, and then 1, we just don't have to factor anything. So next, let's see what we can put them together. Let's see how we can put these together. First of all, for the last column, we notice that all the constant terms are just 1. And again, how many copies of 1s do we get? Since we have n plus 1 rows, we have n plus 1 copies. So we can just write the last term as n plus 1. Great. How about the second to the last column? Well, notice we start with 0, right? But then 0 is not going to affect it. Or in fact, we can just list out in the way we want. We have 0 plus 1, 2, 3, all the way up to n. And since we're adding them together, we actually get the finite sum from k starting from 0 all the way up to the nth term. Meaning we're now having the sum of we have the finite sum of the natural numbers. Except now it starts off with 0 term. Alright? Similarly, we can do the same, similarly, we can add them, we can add the remaining 3 columns together individually to get the following expressions. And again, even we start off with the 0th term, we can just take that away, because if we substitute 0 to any power is just 0, so it's not going to affect the sum itself. So in fact, we can now just rewrite our starting point from 0 into 1, like this. Excellent. So since I'm running out of space, let's erase it, and then we're going to continue our calculations. Alright, so from the last board, we got the following equation. We have n plus 1 to the 5th power is equal to 5 times the finite sum of the 4th power plus 10 times the finite sum of the 3rd power plus 10 times the finite sum of square numbers plus 10 times the finite sum of natural numbers plus n plus 1. Great. What we can do next? Well, if we pay attention carefully, the red part here is actually what we need to find, right? And we actually call it s. So let's relabel it. Meaning now we get n plus 1 to the 5th power equals 5s plus the rest. And what are the rest? Well, we get 10 times the finite sum of the cube numbers, and I've already written aside that the closed form of it is this, n squared times n plus 1 squared all over 4. And similarly, we can just do a substitution for the other two. We get 10 times n plus 1 times 2n plus 1 all over 6. And then for the next term, we'll just get 5 times, what do we get? N times n plus 1 all over 2 plus n plus 1. Don't forget the very last term. Then we can just play around with, we can just manipulate with algebra. So then fortunately, we cannot factor out this, at least in the sense that we cannot put it into, and unfortunately, we cannot factor this out with integer coefficients. So that's it, we cannot make any further. But since we don't start with s on the left-hand side, we have 5s. Let's do our last step. How should we get our 5 from the left-hand side? Since we have multiplication, divide it. So here's our final answer. So we just evaluated the finite sum of the 4th power, which is equal to this expression here. Nice. Pretty cool, huh? Well, so we get the sum s is equal to this expression here. And again, s is what we're trying to find, which is the finite sum of the 4th power from 1 to yeah. So we just found the expression of what s is. Great. And don't forget, s is what we're trying to find, which is the finite sum of the 4th power up to the nth term.